we'll start with resonance. Okay. So we back in Gen Chem 1, we would have briefly talked about resonance in the same sort of section with the Lewis structures and that type of thing. Now, one of the brilliant things about Lewis structures is that it makes it really easy to visualize the connectivity of the atoms when they get together to make molecules. It's pretty, and the rules are pretty straightforward. You use a line to represent 2 electrons, and you use little dots to represent electron lone pairs or non-bonding electrons. And this works really, really great. But there are some inherent problems with it. And so resonance is one of the things where this comes into play. And so we try to we use resonance to basically try to better show how things really are. So if we look at nitromethane here, you've got a nitrogen which has got 4 bonds. So if nitrogen's got 4 bonds, this would mean that from a hybridization perspective, we've got one of these bonds to oxygen would have to be made with p orbitals. So we've got a pi bond here. So we've got 1, 2, 3 sigma bonds, which means we would have 3 hybrid orbitals, which means that this nitrogen would have to be sp2 hybridized because it's got this 1 pi bond. And so in Gen Chem, we learned that double bonds are shorter than single bonds, and triple bonds are even shorter than double bonds. And if we draw nitromethane in this fashion, it would seem to us, if we followed that logic, that the bond between this nitrogen here and this oxygen, this should be actually shorter than this one because this is a double bond and this is a single bond. Or is the actual molecule of nitromethane, like why did we mysteriously choose this oxygen to have the double bond? Why not this one? And so the problem with Lewis structures is that it treats all the electrons like they are a localized species. Said another way, electrons, if they can move between, like, from this oxygen to this oxygen, they will. Often they are delocalized over many atoms as opposed to being localized over, say, 1. And so, like, some electrons are localized. These 2 are here, they're making a bond. But when it comes to when Lewis structures fail is when electrons can be delocalized. So this isn't the true structure of nitromethane, and this isn't the true structure of nitromethane. It's actually a combination of the 2, but we can't draw it because each bond is supposed to represent 2 electrons. And really, what we've got here is that this bond would actually be 1.5, and this bond should be 1.5. This bond should be 1.5, and this bond should be 1.5. So resonance is basically trying to, you draw a series of structures that when you take in combination are supposed to depict what the molecule truly is like, because electrons aren't necessarily localized, they're delocalized. So, and the other part which we haven't drawn, which I didn't even address in the previous part, is where is this negative charge? Is it on this oxygen or is it on this oxygen over here? So when we're doing our formal charge and electron bookkeeping, this negative charge is actually spread over this oxygen and this oxygen. The formal charge for the nitrogen is near the nitrogen. So this isn't the correct structure. This isn't the correct structure, but both of them in combination represent the correct structure, what we will call the resonance hybrid. So both of these two structures are resonance structures of what would be the true resonance hybrid. So the true structure is an intermediate between the two, and we use this wonderful little arrow, the resonance arrow, which has got the two ends to it. This double-headed arrow. And so you would put one resonance structure. I'm trying to get my little laser pointer back. Complications. Okay, so you separate your two resonance structures by a resonance arrow. And so what it's saying is that this structure on one side would be in resonance with the other structure. And to interconvert between the two structures, what we're going to need to do is move electrons. But one of the interesting things is that when you look at an isolated carbon nitrogen double bond, it's basically 116 picometers. If you look at an isolated nitrogen oxygen single bond, it's 130 picometers. But when you measure the bond length of nitromethane, it's 122 picometers. So it's right in between the two. So it's almost like this is 1.5 bonds, but we've got no way of drawing 1.5 bonds, hence resonance structures. But the important part of resonance structures is that it's only the change in location or the placement of pi electrons and non-bonding electrons, so electron lone pairs. And there's a big sort of asterisk here. Excuse me. Drawing. Atoms, the connectivity, hybridization, I better drink something. They all remain exactly the same. So we're not moving anything else except for pi electrons and electron lone pairs. So the hybridization doesn't change, which means the molecular geometry doesn't change. The bond angles don't change. We're not moving like a hydrogen atom from one atom to somewhere else in the molecule. It's only electrons, pi electrons and non-bonding electrons. And so what we're going to see, because it's pi electrons and non-bonding electrons, is that all of the movement is taking place in p orbitals. So this delocalization of electrons is happening in p orbitals. So we're going to have a series of p orbitals lined up together, and the electrons are going to be zipping up and down from one end to the other. So really, resonance is all about p orbitals, because we're only moving pi electrons and non-bonding electrons. We are not using sigma bonds at all. So that's kind of a super important part. So it's the pi electrons and the non-bonding electrons. And so hybridization doesn't change, the connectivity doesn't change, the shape doesn't change. It's just the movement of those types of electrons. So there's some basic rules for resonance. I think there's 5 of them. The first is that the individual resonance structures are imaginary. The real resonance structure is unchanging, and it is the hybrid structure of what we can draw. So it's going to be a hybrid of all of the structures that we can draw. So this is, yeah, so Lewis, all of his little electrons are always localized, and sometimes we need to delocalize them. So this is basically it. So just keep that in mind. So we're going to be drawing some resonance structures, and it's going to give us some practice at moving electrons around. But when we're doing this, we're going to see that it's only the non-bonding electrons and it's only the pi electrons. So second rule, it's only the placement of the pi and non-bonding electrons. So what I've done here is that, so for this resonance structure to interconvert to this resonance structure, we are going to move these non-bonding electrons, and I could have chosen any of the three. There's no specific thing to this. We'll move these two down here to make a pi bond, and then we're going to move these pi electrons up to the oxygen to make a lone pair. So over here, we now have 3 lone pairs on this oxygen. And on the previous oxygen, now we've got a double bond, which means we've got a pi bond. To move back to the way we came, these lone pair electrons are going to move to make the pi bond, and the pi electrons are going to move up to the oxygen to make a set of non-bonding electrons. So the green arrows basically represent lone pairs moving from oxygen to make pi bonds, and the pink arrows represent pi electrons moving to become electron lone pairs on the oxygen. So that is, so rule number 1, basically, what we are drawing aren't real. The true structure is a hybrid of all of the resonance structures. Rule 2, we're only moving the pi electrons and the non-bonding electrons. Rule 3, oh, here's another example. This would be the classic example we used in Gen Chem 1. So benzene. So benzene is a carcinogenic aromatic compound, but it smells so wonderful. But if you're smelling it, you're getting too much of it in your system, so don't smell it, but it does smell good. So it's a series, it's a ring structure with 6 carbons, and we've got alternating pi and sigma bonds, but of course that's not the real structure. All of these bond lengths would, when you do the spectroscopy and calculations on it, they're all 1.5. So this isn't the real structure. This isn't the real structure. The real structure is a hybrid of the two. But basically these pi electrons are rotating around the ring. So in this case, these pi electrons, are going to make a bond here to here. And so the bonds are, it's just zooming around the ring. All right. So that was rule number 2. Rule number 3 is that resonance structures don't need to be equivalent. All of the previous examples we've done, you could say, like, in other ways, but some people would view this as just that they've rotated this through this bond here to make that. But remember, with resonance structures, it doesn't involve rotation or movement of sigma bonds or any atoms. There's no movement of atoms at all. But I know that some people visualize this way because it's a common sort of mistake. So it's only the movement of the lone pair electrons and pi electrons. And here you could say, well, these two things look at like exactly the same. But resonance structures don't need to be equivalent. So in this structure here, we've got oxygen with a negative charge. And in this resonance structure, we've got carbon with a negative charge. So they're not equivalent. These lone pairs move here to make a pi bond. The pi bond electrons move to carbon to make a lone pair. And so if we do a formal charge on a carbon with 3 bonds in a lone pair, the formal charge is minus. We do the formal charge on oxygen with 1 bond and 3 lone pairs, it's a minus. So this negative charge is delocalized from oxygen to carbon. Now, actually, this is an excellent part where I could ask a question. And that question is, Which of these two structures, the one on the left or the one on the right, which one do you think contributes more to the resonance hybrid? Because they don't need to contribute an equal amount. That's part of this. So they don't need to be equivalent, and they don't need to contribute an equal amount to the hybrid. So one resonance structure might contribute 80%, and the other one might contribute 20%, for example. Which one do you think it might be? The one on the left or the one on the right? I should have put a little question here. Bunch of people saying the one on the left. You are correct. Okay, so why did you intuitively think that the one on the left contributed more to the resonance hybrid? And this has to do with electronegativity. Right, okay, so when we think back to our electronegativity, oxygen is more electronegative than carbon. So, and this is going to become really important later on in the next section on acids and bases. So if oxygen is more electronegative, its ability to stabilize that negative charge is better than carbon. So the electrons are delocalized between the two atoms. But this resonance, when you do the calculations on this sort of system, you'll see that there is more electron density on this oxygen than there is on the carbon, because oxygen's more electronegative. But these lone pairs are delocalized onto this carbon as well. So they are there, but it's just that this one contributes more to the hybrid. So this system here is what we call enolate, and it's used in synthetic organic chemistry all the time. So, but they don't have to be equivalent. That's the other rule. Excellent, excellent, excellent. Okay, so the fourth rule is that you'll notice that when we were moving lone pair electrons to make pi bonds and then moving pi electrons to make lone pairs, when we move these here, these go up. We can't have, our resonance structures have to be valid Lewis structures. So at no point did I just move these electrons here and make a structure which looks like this. The problem with this structure over here is that, and it was the same with nitromethane as well. The problem with this structure here is carbon's got 1, 2, 3, 4, 5 bonds, which means would have 10 electrons. And remember the octet rule, carbon can only have 8 electrons. So it has to be a valid Lewis structure to be a resonance structure. So when these electron lone pairs move to make a pi bond here, that means that this pi bond has to move to make a lone pair electrons. The other thing that you will have noticed throughout this whole process is that negative charge here, negative charge here. Whatever your charges are on your structure, if it's a neutral structure overall, it doesn't mean it can have a positive and a negative in it. But overall, it's still going to come out being neutral. If your structure's got a negative, your other resonance structures should have a formal charge of negative. Okay? So all resonance structures have to be valid Lewis structures for this to work. Okay, and then the fifth one is that the resonance hybrid is more stable than any of the individual resonance structures. So in the previous example where we had this unequivalent system where we have the more electronegative oxygen versus the carbon with the negative charge over here, the hybrid of these two is more stable than either one of these. And that's because when you delocalize these electrons, like resonance leads to stability, or resonance provides stability. Any molecule which has got a multitude of resonance structures are going to be more stable than molecules that don't. Like in the, so yeah, resonance leads to stability. So when you spread whatever charge or electron density over numerous atoms, we call this basically delocalization. And that provides stability for the system. So, and so when we're delocalizing electron density, this is where the power of molecular orbital theory comes into, because in molecular orbital theory, the whole point is that the electrons are throughout an entire molecule, as opposed to like in Lewis structures where it's all localized. So, but it's so easy to read Lewis structures. That's why we use them, easy to draw them. So we just have to, when we come into a case where we've got Lewis resonance structures, we need to be able to interconvert them. So the take-home message for this section is resonance leads to stability, or provides stability. Now, 9:43. We've got about 5 minutes left. The next part of this is gonna be about hints and tips for drawing resonance structures. It's probably best not to start that right away. Kind of want to do a little review here and answer any questions if people have any of what we've covered so far. So the next thing what we're going to do on Thursday is basically go through pattern recognition for drawing resonance structures. Probably out of all of the review material, the hardest thing is resonance structures, because we barely skim the surface of it in Gen Chem, and it plays such a crucial and critical role in what we're going to do throughout the rest of, particularly in the acid and base section. Like, we use it all the time. So let's see here. There was a chat question. Yes, so here we go. Let me